Hello, my name is Brett Yule, and in this video is pretty much a continuation of the previous video. We will be going over how this model data fits the Antoine equation. So also another thing I realized I did wrong in the last video is this right here. These are supposed to have a blue line. This A is not supposed to be here. So now they should be blue. Yes, so now they are blue. So what I'm going to do is I'm going to input some real values for the Antoine equation. So we'll make A 8.07131. We'll make B equal to 1,730.63. C equal to 233.426. And what I'm going to do is these are actual values to check our data. So I'm actually going to make this a capital C for check. So what we're going to do is we're going to plug these values into the Antoine equation using our actual results. So what we'll do is log, oh shoot, wrong thing, EV minus A minus B. So pretty much what we are doing here, log PV represents each of these values of points. And the second part right here is the actual Antoine equation. So since these are real life values, if we subtract this from this, they should equal about 0. So now what we'll do is we will print check, shift enter, and as you can tell, all of these values are about 0, but not exactly. But that's fine because that was just a general estimation to see if they actually are. So what if we don't really know the values of A, B, and C? Well, we can make guesses. So let's say our guess for A is about 10. Our guess for B is about 2,000. And our guess, misspelled guess, our guess for C is 0. So essentially what we will do, well, what we can do is store, we can make a thing called x0, which is just a random value. And what we're going to do is store these as a list of num. And all right, everything worked there. So now what we're going to do is we're going to make some functions. The first function we will call square error. We will need T, S, and log P, B. So essentially what this is doing is to help determine the error between the ideal model and the actual model. So we will define ideal model as this. First brackets, there it is. and we will define the error. So I'm trying to get this out of the way. There we go. Now we can see it better. So here, the function name is square error. Here's the error. And what we are doing is we are taking the ideal model and subtracting the log and then squaring it, which is hence square error. So now what we will do is we will return the error. Let's see, all the syntax is right. All right. So now we will go on to the next part. So what this minimize function does, make sure I spelled it right, it pretty much causes minimization of the scalar function with one or more variables. So what we will do is we will have square error, not capitalized. And this TOL stands for tolerance. Oh, that's not 10. There we go. So then shift enter. Up, nope, something's wrong. What is wrong? So it says here, let's see if uncapitalizing it helps. No, it does not. Wait, now it says invalid syntax. That's weird. I have to look at my notes to figure out what I did wrong here. I honestly don't know why this is wrong. let me retype this, see if that helps at all. Alright, let's see if this works now. No. So again, it says the name model is not defined. I see. Yeah, so what I did wrong, I missed adding a function right here. Can't remember how to add a cell after something. Alright, so what I forgot to do was define the model, which is why it was saying model is not defined, because I forgot to define the model. Alright, here we go. Now that we have the model, now that we have this model defined, which is the Antoine equation right here, this is now defined, which fixes the term model not being defined. Whew, man, that was a struggle. So now what we will do is begin working on actual scatter plot stuff. So our ideal temperature, JP in space, no, I did, no, the zeros in brackets, there we go. So what this does is it creates a numeric sequence for the ideal temperature. So now what we will do is add a scatter, in which I'll describe all the axes and labeling stuff at the end, so that way it's just all simpler. All right, so what this does is we are making the x-axis equal to the ideal temperature, the y-axis equal to the model function from right here. The mode is lines, so what this will do is, contrary to this one, which we set the mode to markers, the lines will obviously make a line, and line width just refers to the size of the line, and we are naming this Antoine example. Actually, well, I'll do this capitalize D because it's bothering me personally. So now, if we hit Shift Enter, it is off, which means I made an error. Because what's supposed to happen is this line is supposed to be with the data. So I definitely made an error somewhere. Let me try and figure it out by looking at my notes. Let me first make sure I hit Shift Enter on all of these cells, because sometimes that can affect it. All right, now it's all right. So something is definitely wrong in the code for it to do that. Sorry, my power just flickered for some reason. Let me see if this fixes anything. I doubt it. Yeah. Which that is definitely not what we want. It's probably something. Yes, that will do it. I did not make this capital A right here. I was just about to say it's probably something simple. Here we go. All right. So, first of all, zoomed in on accident. As you can see, something as simple as typing a lowercase a here rather than capital completely threw off my results. This is actually what it's supposed to look like. So you can tell how our actual experimental data relates to what it should be. So this is how you apply the Antoine equation to actual real-life results.